The exam was a difficult exam. It was a little, I think, too long. The median and mean turned out to be 75%, and the grades were distributed as follows. So I think if you were in the 70s or above, you're doing fine. Down here, I think you need to do a little bit of work just to practice doing these kind of problems. I realize we don't have time pressure on homework, and I may try to design the second hour exam to relieve a little time pressure. We'll see what we can do. So let me just go over the questions briefly. I think the problem one number of people had a difficulty with, the definition of a cyclic group means there exists, G is cyclic, if there is an element, G in G, such that any, well, let's call this element A maybe, the generator, such that any G in G has the form G is equal to A to the n, some n in Z. So any element is some power of G. Such G's are called generators. Do not think, and this is where people made a mistake on the second half of the problem, that any element of the group is a generator. That's not true. For a cyclic group of order 4, the square of a generator is not a generator because it has order 2. So the definition of a cyclic group, there should be some generator of this form. And then you're supposed to prove that if H is a subgroup of G, is also cyclic. So what we have to find for H is a generator of H, given the fact that A is a generator for G. Let's write it like this. So there are two possibilities. If H is equal to the identity, then it's true. Because the identity group is, by definition, cyclic. You can take the identity element as a generator. If not, then H contains A to the n for some n bigger than 1, or equal to 1. Because if it's not just the identity element, then it contains some power of A for some non-zero integer. And if it contains some non-zero integer, then by taking the inverse of that element, you can assume that it contains a power of A for some positive integer, taking inverse if necessary. And then what you do to find a generator of H is a generator B of H is A to the k, where k is the minimal such power, such n. Namely, for all the positive powers of A that lie in H, take the smallest positive power of A that lies in H, call that thing B, and I claim that B generates H. So now you have to prove that. So you say, well, suppose there's something else in H. Say A to the m is in H. So we write m as some multiple of k plus a remainder with 0 less than or equal to r less than k. We use the Euclidean algorithm to write it that way. Since A to the m and A to the k to the qth power are both in H, so is A to the r. But r is a positive number less than k. And the only positive power of A, by definition of what k is, that lies in H, or non-negative power of A that lies in H, is the 0th power. That implies that r is equal to 0, so that m is equal to q times k, and A to the m is equal to b to the q. And that shows that any element in H is a power of the smallest power of A that lies in H, so that H is also cyclic. It's not true that anything in H will be a generator. So that was a mistake that a lot of people made. Yeah, Atticus.
When you say H contains A to the n, do you actually mean H has the element A to the n?
Yeah, sorry, like that. Yeah. There's some power of A that lies in H if it's not the identity. All right, number 2. So the first thing is if H is normal, show that GHG is equal to, sorry, HGH, sorry, is a left coset. Well, if H is normal, that implies for every G and G that GH is equal to HG as a set. That the left coset of G is the right coset of G. So you simply replace this HG here by, it's the same as the set GH times H, but GH times H by associativity is the same thing as G times H because anything in H times anything in H lies in H, so that shows it's a left coset. And the second part of this problem is a little harder. You're supposed to say, if H is not normal, then this is not equal to GH. So let's do it this way. If HGH is a left coset, we're going to prove that H is a normal subgroup. Well, if it is a left coset, it must be the coset GH. Because it contains that coset. If you take the first element in H to be the identity element, and you take the identity, because this is equal to E times GH, and E is an element in H. So because it contains this set. So there's only one possible coset it could be. So on the other hand, so HGH has to equal the set GH. Now, what this means, if you so I claim that means that if you take this right coset, this implies that H times G is actually contained in GH. Because this is a subset of this. Namely, this is H times G times the identity. So that this right coset is contained in this left coset. In particular, conjugating by G, G inverse HG is contained in H. Well, that's true for every G. Because this is assumed to be a left coset for all G and G. But that implies, in fact, that G inverse HG is equal to H for all G. Because take this identity and multiply it on the left by G and on the right by G inverse, you get H is contained in GH G inverse for all G. Conjugate by G. And if this is contained in this and this is contained in this for all G, then this is contained in this, which is contained in the same thing for G replaced by G inverse, so they have to be equal. And this means that H is normal. So if this were a left coset for all G, then we've just proved that H is normal. So if it isn't normal, there has to be some G for which this isn't a left coset. Okay? The third problem most people got, it wasn't that hard. It's really a definition of what it means to be equal in a quotient group. So the third problem, suppose if x bar commutes with y bar in G mod n, which is G bar, that's just the statement that the coset xy is the same as the coset yx. So this is an equivalent way of stating it. Because this is what x bar times y bar is as a coset, and this is what y bar x bar is as a coset. But this is the same thing if you multiply. Let's see how we do this. Let's multiply on the left by x inverse. Yn is equal to x inverse yxn. And then multiply on the left by y inverse. N is equal to y inverse x yxn. And if the coset of this is n, that means that this is an element in n. Did I do this right? Is that what we were supposed to prove? Oh, I think I did it the other way around. Sorry. I apologize. Let's do it again. So let's instead multiply this by y inverse, so I get exactly the statement that I put up. Apologies, I did it the wrong way. Y inverse xy n is equal to xn, and then that's the same thing as x inverse y inverse xy n is equal to n, which is the same thing as x inverse y inverse xy is in n. And all these steps are reversible, so that's the problem 3. Now this element is sometimes called the commutator of x and y. You'll see it in the literature written that way. Okay, that's problem 3. Problem 4, people got the definition of the center right, but then had trouble with the rest of the problem. So the definition of the center consists of all elements z, such that zg is equal to gz for all g and z. The things that commute with every element. Now, suppose you have a unique element of order 2. First of all, if z, let's say A has order 2 in G, then I claim that GA J inverse has order 2. The conjugate of any element of order 2 has order 2. In particular, in general, the conjugate of an element of order n has order n. Conjugation is an automorphism of the group, so it preserves everything, like order. Well, you can prove this rather easily. You just square the element. And these two things cancel, so you get g a squared g inverse, which is just g inverse, because a squared is 1, which is e, which shows that the square of this element is 1. But this element can't be 1 because you can't conjugate a non-trivial element into the identity. So it has order 2. Well, if it has order 2 and there's a unique element of order 2, and this is what most people didn't use in the problem, you can't just get it out of the fact that the conjugate has order 2. If A is unique, that implies that GA, G inverse, is equal to A for all G. Because it's another element of order 2, which means that GA is equal to AG for all G, which implies that A is in the center. This argument, by the way, is the argument you can use to show that the conjugate of an element of order n has order n. Again, you multiply it n times. N times. And then all the internal g's and g inverses cancel, and you get g a to the n, g inverse, which is the identity, if a to the n is the identity. And then you can do that for all g, so that shows that it has exact order n. Okay, so this is unique. Can you have a unique element of order 3? So almost everyone got that. You can't, because if you have an element of order 3, it generates a cyclic group of order 3. So you get a little subgroup that looks like a squared, and you find that this element also has order 3. In fact, a squared is the same as a inverse. A and a inverse always have the same order. So the only way it could possibly be unique is if a is equal to a inverse, which means that a has to have order 2. If you have an element of order 4, it can't be unique. An element of order 5 can't be unique. So that's a is not equal to a squared, so you can't have the unique element of order 3. But these elements frequently come up. We're going to see groups which have unique elements of order 2, so you get an interesting element in the center. Okay. Problem 4, almost everyone got. That was the question on the symmetric matrices. So I'll just, so if A is equal to Aij, where Aij is Aji, this is clearly closed under addition and scalar multiplication, and contains the 0 element, so it's a subspace. That was easy. And then the dimension isn't hard either, because if you think about it, such a matrix is completely determined by the entries on the diagonal and above the diagonal. Once you have these entries of the matrix, they determine everything else. So you just have to count how many possibilities are there for matrices on the diagonal, etc. And the number of entries in this diagonal is n, and here we have n minus 1 entries, and here we have n minus 2 entries, all the way down to 1 entry. So the dimension is 1 plus 2 plus n, which is n times n plus 1 over 2, a little bit more than n squared. Okay. And problem 6, most people got, oh, I'm sorry, then you have to, I asked whether it was closed under multiplication, so I got all kinds of abstract arguments here, but all you have to do is write down an example. So an example, if you do this, if you multiply this by this matrix, these are both symmetric matrices, but when you take the matrix product, you get this, which is not symmetric. Some people gave me the general 2 by 2 times the general 2 by 2. They got a 2 by 2 matrix here, and they said, well, it doesn't look equal, but I don't know that. I mean, it's some funny combinations of A's and B's. You actually have to give me numbers. Other people said, well, if it were closed under multiplication, then by taking transpose, I would have AB is equal to BA for all elements in the group. And since we know matrix multiplication isn't commutative, then that can't happen. Well, we don't know that symmetric matrix multiplication isn't commutative. It's a picky point. But it's so much easier when you're trying to give a counterexample to a statement, just give an example. Less theory. When you're trying to prove something, that's when you need theory. Okay? And then finally problem 6, which almost everyone realized. Once you wrote down the bijection, it was pretty clear. So we had the vector space f to the n. And we want to give a bijection between the set of bases and GLNF. So first of all, most people forgot the first part of the problem to actually define this group. I didn't take too much off. But this is going to be the set of A, which are n by n matrices with entries in F and determinant of A not equal to 0 under multiplication. That's the definition of the group GLNF. And we want to map between bases and elements in GLNF. And the idea is if you take a basis, an ordered basis V1, Vn, and you define f of that basis to be the matrix where the first column is the entries of V1 and the second column is the entries of V2 and the last column is the entries of Vn. That gives you an n by n matrix. Since these elements are linearly independent, because it's a basis, these columns are linearly independent, so that people could quote shows that the determinant of the matrix is non-zero. So that's a map between bases and elements in GLNF. It's clearly a one-to-one map because if you know what the matrix is, you know all the entries of the basis, so you know the basis. No two bases would go to the same matrix. And it's onto because if I take any invertible matrix and I just can take the first column as my first basis vector in Fn, and the second column is my second basis vector. The fact that the matrix is invertible says that the elements, these n elements, are linearly independent, so give a basis. That was all I needed for that. Now, for those of you who tried the last one, and there were 1 or 2 people who tried it, I'm not sure anyone, or 1 or 2 people got it, you use this problem to do it. That's the best way to do it, namely to calculate the order of the group GLN of Z mod PZ. You have to calculate the number of ordered bases of Z mod PZ to the nth power. Well, why would that be any easier than calculating this? Well, let's try to make a basis. The first thing we have to do is choose our first basis vector. So that's got to be a vector in this space. And the only thing it has to be is linearly independent from 0. We're going to build a basis by keeping adding linearly independent elements. So the first thing is just some non-zero vector in there. And there are p to the n minus 1 choices for that first vector. Right? Because there are p to the n vectors here, and only 1 is 0. And then if we're going to make we have to choose a basis vector v2, we want it linearly independent from v1, i.e. not on the line spanned by v1. So there are p to the n total vectors in here, and there are p vectors on the line spanned by v1, so there are p to the n minus p choices for v2. And then if we want to choose V3, it better be linearly independent from the plane spanned by V1 and V2. And there are p to the n minus p squared choices for the vector V3, because there are p to the n vectors total, and these are the number of vectors in the plane spanned by V1 and V2. We keep going down, and the last best vector is p to the n minus p to the n minus 1. So the total number of bases is the product of this number of choices times this number of choices times this times this. So it's p to the n minus 1, sorry, p to the n minus 1, p to the n minus p, down to p to the n minus p to the n minus 1. And if you factor out all the powers of p you get p to the n times n minus 1 over 2 times p to the n minus 1, p to the n minus 1 minus 1, down to p minus 1. So in particular, if you wanted to do the order of the finite group GL2 over Z mod P, 2 by 2 invertible matrices, it would be P times P squared minus 1 times P minus 1. We're going to come back to this finite group later. It's an important group to do. And the best way to count its order is to use this bijection of sets, namely to forget that it's a group and to think of it as counting the number of ways of assembling a basis of this vector space. There was no extra credit given for that, but I thought you might find it amusing if you had time. Nobody had any time. So I will try to, as I say, construct the next exam so that it not only tests the material, but gives you enough time to think about it. Many people complain that they just were sort of too frazzled, and I know the feeling. I'm very slow myself, so I will try to set it up. Questions about this? Do not get discouraged. I don't think anybody in the course is seriously lost. This is all a process of learning a language. If you're, as I say, if you're in this range, you're doing fine. If you're down here, I think you need a little bit more practice. Okay, now we're going to get started, and we're going to, with the linear algebra that we have at our disposal, we're going to go back and construct some very interesting groups and start to study a beautiful relationship that was discovered at the end of the 19th century between group theory and geometry. Almost all of geometry is now formulated in terms of group theory. Many of you may have been reading in the popular science press, some mathematicians and astronomers have come up with a model for the shape of the universe, which is all based on group theory, based on a dodecahedron. The universe is a soccer ball. Anyhow, I don't actually believe their model, and I think that when they look at a little bit more data that's come in from the various radio telescopes that are orbiting, that they'll contradict it, but it's an interesting hypothesis.
Do you think that the universe looks like a dodecahedron?
Yeah, that it's finite and that you should be able to look out in this direction and see something that you saw back in that direction. Yeah, if you look on the... Do they really believe it? Yeah, there's an article in... No. Kepler had this wonderful model where... Yeah, but Kepler also believed, for all of his science, he believed that the solar system was organized by inscribing Platonic solids into other Platonic solids. I mean, there was a lot of mysticism back then. So mathematicians still believe that there should be some very simple three-dimensional geometric shape that describes a finite universe. And the astronomers keep coming up with data that contradict this. But never mind their data. So if you look on the cover of, I believe, Nature, in which the article is published this month, there's a description of it. I know the guy who wrote the article, Bill Meeks. He's been proposing this for some time. And they're just getting enough data from all these orbiting satellites to actually test it. Okay, now we have this group that I call GLN of F for any field. Now we're going to define a very interesting subgroup of it, which I'm going to call ON of F. And then we're going to define a subgroup of that, which I'm going to call SON of F. And that works for any field. And we're going to show that they have some interesting matrices in it. And then we're going to take a look at this when F is equal to R. It's related to geometry. In fact, Euclidean geometry. This group, by the way, this sometimes is called the general linear group. These are called the orthogonal groups. That's why the O. And this SO stands for special orthogonal group. You'll see what that is. That's a normal subgroup of the orthogonal group. And in fact, the index is 2, so it's rather simple. Okay, so here's the definition of this group. The first thing we do is we take our vector space V, which is f to the n, and this group is just the linear maps from V to V, which are isomorphisms. So we're going to get a subgroup by putting some more structure on V, some more structure, and then just looking at the subgroup that preserves that structure. So we put additional structure on V, and the structure we're going to put on it is an inner product. We're going to take two vectors and give you a scalar. So, when you take courses in calculus, these things are called inner products. More generally, they're called bilinear forms. All right, so we're going to define an extra thing that takes two vectors and coughs up a scalar. And here's the definition. The vector itself is an n-tuple of elements in F. And the vector W is an n-tuple of elements in F. And the definition of this inner product is what you did in calculus. A1, B1 plus A2, B2 plus AN, BN. So it's some weird form of the product. You take the product of the first two elements, then you add it to the product of the second two elements, then you add it to the product of the third. If we were just in a one-dimensional vector space, it would be the product. It would just be A1 times B1. Okay. And we define ON to be the elements A in GLNF that preserve the inner product, such that when you take the inner product of AV with AW, it's the same as the inner product of V with W. That looks like a weird thing to do. But I claim that this is a subgroup. So everyone, AV means you apply the matrix A to the vector V and you get another vector. You multiply, right? So this would really be A times V transpose if you really wanted to write it that way. I mean, but I want everyone understands what I mean by AV. This is the vector, A times V transpose, something like that, right? You line up the vector, you multiply it by May, and then you straighten it out again. Okay, so why is this a subgroup? Well, because if I have, it certainly contains the identity element. If it contains A and B, is it true that AB of V, AB of W, is that equal to VW? Well, let's see. This is A of BV, A of BW, because matrix multiplication is composition of operators. Now, this is since A is in the orthogonal group, this is the inner product of BV with BW, because if we apply A to any vectors, we don't change their inner product. And then since B is in the orthogonal group, this is the inner product of V with W. So if A and B are both in the orthogonal group, so is their product. And I'll let you check inverse. It's no harder. Okay? Also, A inverse is in O of N of F. All right, now let's figure out what this means in terms of what the matrix looks like. Now remember, what the matrix looks like is this. The matrix A has first column what the operator A does to the vector A of the vector 1, 0, 0. And the second column of A is what A does to the vector 0, 1, 0, 0. And the last column of it is what A does to the vector 0, 0, 0, 1. Because this vector space has a standard basis, and the standard basis we'll call E1, which looks like 1, 0, 0, 0, 0, down to En equals 0, 0, 1 in the nth place. That's the standard basis of this vector space. And you turn a matrix into an operator by seeing what it does to the standard basis. Okay, now the standard basis has the following property. If you take the inner product of E1 with itself, you get 1. And you take the inner product of E2 with itself, you get 1. And you take the inner product of En with itself, you get 1, right? Because these only have one 1 in them. And if you look at this formula, only one term is non-zero, and it's 1 times 1. On the other hand, if you take the inner product of EI with EJ, and I is not equal to j, you get 0, because EI has a 1 in the ith place, and EJ has a 1 in the jth place, and you get zeros in all these terms. So, that has to be true for these column vectors too, because we preserve the inner product. That's the definition of what it means to be in the orthogonal group. So if you take the inner product of this column with itself, you have to get 1. And the inner product of this column with itself, you have to get 1, because that's the same as the inner product of E2 with E2. All right? What does the inner product of this column with itself look like? Well, it's this element squared plus this element squared plus this element squared, right? The inner product of this column with this column is this element times this element, this element times this element, this element times this element, this element. Okay? Now, we can rewrite that in the following way. This implies that the inner product of A, EI, A, EJ equals product of inner product of ith and jth columns equals 1 if I is equal to j, and 0 if I is not equal to j. Okay, now let's rewrite what this means. This is n squared different numbers that we know. N numbers we know are equal to 1, and a lot of numbers we know are equal to 0. I claim that this is the same thing as saying that if you take the transpose of the matrix A and you multiply it by the matrix A, you get the identity matrix. Well, let's see why that would be the case. Suppose we took the transpose of the matrix A. The first row of that is A of 1, 0, 0, 0. Right? Because the first row of the transpose is the first column here. All right? Now let's calculate the first entry in A transpose A. Let's calculate this entry up here. We go across the first row of A transpose. We go down the first column of A, and we add up. Well, that's just the inner product of this column with itself. And we agreed that was 1. So the first entry here is a 1. Let's calculate this entry here, the entry in the first row, second column. We'd go across the first row here, and we'd go down the second column here. Well, that would be the inner product of this column with this column, which we agreed was 0. So we get a 0, etc. You get zeros all here. Then when you did this row, you'd get a 1 there. And you'd see that this matrix product times this is the identity. That's just another way of rewriting that the columns have this property. So we see that if we have a matrix in GLN which preserves the inner product, then the product of the transpose of the matrix by A is the identity, which is the same thing as saying that the transpose of A is the inverse of A. So it's also true in the other direction. A times A transpose is the identity. Okay. Conversely, I claim that if we have a matrix such that the product of its transpose times the matrix is the identity, or the matrix transposes its inverse, then it gives a transformation that preserves the inner product. Let's check that. That's a little tricky. If A in GLNF has A transpose equal to A inverse, then it preserves the inner product. We have defined on the vector space V is equal to Fn. So that's the matricial form of this preserving the inner product. Matrices whose transpose are their inverse. Why? Well, this is quite tricky. So let's see. Well, first of all, I'm going to rewrite the inner product, VW, as a matrix product. It's just the transpose of the vector V times the vector W, where this becomes a column vector and this becomes a row vector. I mean, if you think of it, that's exactly what the inner product is. If you tried to multiply, whoops, other way around, huh? I want, well, let's see. No, I want a row vector and a column vector, sorry. Let's try it this way. I hope I don't get totally screwed up here, but we'll see. So we write the vector V like this, we write the vector W like this, we go across this row and down this column, we multiply the first entry times the first entry, we multiply the second entry times the second entry, the third entry by the third entry. That's exactly what we're doing when we're taking the inner product. So this is a matrix product. Okay, now on the other hand, let's see if we can compute AV, AW. Okay, so AV, oh God, this is going to be a real nightmare because I've written my vectors as, never mind, let's go back. Let's write our vectors as column vectors so I don't actually kill myself here. So this would then be V transpose times W, where I thought of the vectors as column vectors. I now know why I want to do that. Because then AV, this vector is just the matrix A times the column vector V. And this vector is just the matrix A times the column vector W. And consequently, the inner product would be, you'd calculate this vector, you'd transpose it, and then you'd multiply it by this vector as matrix multiplication. This is all matrix multiplication, A times V transpose. Then, now if you know about transpose, that reverses the order of matrix multiplication, so this becomes V transpose, A transpose, A, W. And if we assume that A has its transpose is equal to its inverse, this is the vector V transpose times the identity matrix size n times the vector W. The identity matrix takes any vector to itself, so this becomes V transpose times W, which is the same as VW. That's why I want to take my vectors to be column vectors. Just, I don't have to write transpose 8 million times. If I take vectors to be column vectors, this is just A times V. So in other words, this can also be written as the set of A in GLNF such that A transpose is equal to A inverse. Okay, now I'm going to show you a number of interesting things that happen with these matrices. For example, the first thing is that the determinant is not arbitrary. I claim that the determinant of A has to be plus or minus 1. Because if you take the determinant on this identity, you get the determinant of A transpose times the determinant of A is 1. The determinant of A transpose is the same as the determinant of A. So the determinant of A squared is 1. So the determinant of A has to be plus or minus 1. Of course, these things might be equal in the field. I want you to recognize that. I mean, if we had the field of 2 elements, they would be equal. But at least it's a plus or minus 1. Its square is 1. Okay? So you might ask, do we get both determinants in our group? And the answer is yes. So to do that, you have to actually exhibit elements in this group. So I'll show you some elements which happen to preserve the inner product. And maybe the only thing in the group is 1. But if you take this matrix, for example, any matrix that looks like plus or minus 1s on the diagonal and 0s elsewhere, that's an element in ON of F. Because if you calculate its inverse, it's equal to its inverse, and it's also equal to its transpose. Yeah?
So is every matrix in GLN F3 also in ON F3?
No. In GLN of...
Oh, never mind, because it's not a...
Okay. This is just a necessary condition. It's not that every matrix with determinant 1 is in ON, but any matrix in ON has determinant plus or minus 1. So these are examples of matrices in ON of F. They're rather stupid because not only is the inverse equal to the transpose, but they're equal to the original matrix. And in particular, if you took the matrix that looked like this, minus 1 plus 1, plus 1 down the diagonal, you'd find the determinant of this is equal to minus 1. So you can have both determinants plus 1 and minus 1. In particular, you get a subgroup where the determinant is plus 1. That's this group. A in ONF, such that the determinant of A is equal to plus 1. And that's a group of index 2 because if you think of the determinant as a homomorphism, you get a homomorphism, the determinant, to the group of order 2 plus or minus 1, which is onto, because you have things of both determinant 1 and plus or minus 1. It's a homomorphism because the determinant of AB is the determinant of A times the determinant of B. And this group is just its kernel. And the kernel, we know by the isomorphism theorem, the index of the kernel, the quotient group, is the image. The image is plus or minus 1, so there are exactly 2 cosets of this group in this group. And the kernel is a normal subgroup. And the cosets are the elements of determinant 1, that's this, and the non-trivial coset, namely this times SON. What other elements are in ONS? Well, I claim the permutation matrices are in ON of F, and this gives injective injective homomorphism F from the symmetric group on n letters into ON of F, no kernel, and that takes the subgroup, which is the alternating group on n letters, into SON of F. I better assume that 2 is not equal to, 1 is not equal to minus 1 in F. For this, I should have said that. This subgroup, if 1 is equal to minus 1 in F, i.e. if F is equal to Z mod 2, 1 is equal to minus 1, then this homomorphism is not surjective. It only maps to plus 1. And so ON and SON are the same group. So if I really want to get a different group, the index of 2, that's if 1 is not equal to minus 1. So the permutation matrices, I claim, are orthogonal matrices. Why? They have exactly one in each column, and the rest are zeros. Therefore, if you think of it in terms of this thing, they preserve the inner product on the basis elements. Namely, the columns are of inner product with themselves 1 and inner product with the other column 0. Yeah?
Would you mind just explaining the connection of the isomorphism theorem?
Sure. We have a homomorphism. Well, let's assume that 1 is not minus 1. So we have 2 elements, plus or minus 1. This is a subgroup of F, of the multiplicative group of F. The determinant maps these matrices into this group. It's a homomorphism because the determinant of a product of a matrices is the product of the determinants. It's onto because we've exhibited a specific element in the orthogonal group whose determinant is minus 1. It's onto. There are elements in this group that have determinant plus 1, and there are elements that have determinant minus 1.
Okay, so you have to show that it...
Here's an element of determinant minus 1, and the determinant of the identity is 1.
Right.
So our isomorphism theorem says that the quotient group by the kernel is isomorphic to the image of the homomorphism. The kernel is, by definition, this group. That's the definition of it. The things that...
Those are just things that map to 1.
The 1, the identity element in this group. And therefore, the quotient group has order 2. And therefore, there are 2 cosets, so the index is 2. So I claim that if you have a permutation matrix, it does preserve the inner product. And this definition of the alternating group is exactly what we said. It's the permutation matrices whose determinant is 1. So that's really how we got the alternating group out of the symmetric group. And this is injective because any permutation is determined by its n by n matrix. So this is a nice finite subgroup of the orthogonal group over any field. Okay, so much for the orthogonal group over an arbitrary field. What's particularly nice about the real numbers is this inner product is set up to do Euclidean geometry. What's so cool about this inner product is that the inner product of V with itself is the sum of AI squared from I equal 1 to n, right? And that sum of squares is bigger than or equal to 0. You see, this kind of expression makes absolutely no sense in a general field. You can't say whether an element in Z mod 3 is bigger than or equal to 0. But in the real numbers, we have this notion of positive and negative, and all the squares are positive, right? So this sum is bigger than or equal to 0, and VV is equal to 0 only when V is the 0 vector. Because if any coordinate in V is non-zero, this sum is positive. And so we define the norm of V, or the length of V, to be the square root, the positive square root of VV. And this generalizes our notion of the Euclidean distance of the vector, because if we were in R2 and we had our vector here, which was the vector AB, where we'd go over A units here and up B units here, then the length of this line segment is the square root of A squared plus B squared by the Pythagorean theorem. And consequently, this length measures the distance of the vector V from the origin in 2 space. And we define a geometry in general by saying that's the length of the vector from the origin, the square root of the sum of the squares. Okay, and we can also, and this is another thing that you probably have studied in calculus, you can use it to not only define the length of a vector, but you can use it to find the angle between 2 vectors by writing that it's an interesting inequality that VW, there's something called the Cauchy-Schwarz inequality, which I won't prove here, that says that if you take the quotient of VW by the norm of V times the norm of W, assuming that V and W are both non-zero vectors, so that these norms are non-zero and you can divide by them, you get a real number. This is a real number. These are positive real numbers. And this real number lies between -1 and +1. So that this real number can be written as the cosine of theta for an angle theta that lies between 0 and pi. And that angle theta is called the angle between the 2 vectors. And it doesn't depend on the ordering of the 2 vectors because this pairing is a symmetric pairing. VW is the same as WV. So not only does this wonderful fact that the inner product of a vector with itself is non-zero and positive give you the length, but the Cauchy-Schwarz inequality gives you, from 2 vectors, an angle that lies between 0 and pi that you say is the angle between 2 vectors. And that comes from the law of cosines in the 2-dimensional case, that if you had 2 vectors, V and W, and you computed this ratio, the angle theta would be that angle there. So this lets you, if you have a real vector space and you give it this additional structure of the inner product, it lets you define lengths of vectors, it lets you define angles between vectors, and this is what's critical for our point of view, the group ONR acts linearly on R to the n, and it preserves the length and angle. Because it preserves inner products, so therefore it preserves anything we can get out of an inner product. One moment, I'm just going to finish this, then I'll take questions. And therefore it preserves the notions of Euclidean geometry, namely it would take If you had a triangle and it was based in the origin, it would take it to another triangle. And you have this angle theta and you have VW. It would have to take it to another triangle based at the origin where the side lengths were the same as these two side lengths, and this angle would be the same, and so it would have to take it to a congruent triangle. It can't stretch things, and it can't bend angles and things. It preserves somehow the Euclidean geometry. Now I'll take the question. I'm sorry.
We're like assuming that we have a notion of cosine in order to define.
Oh, I'm sorry. We're using the fact that any number that the cosine of on this interval maps this interval uniquely into this interval. You know, is that as we go. Oh, I'm getting a telephone call. That the cosine from starts like this and goes like this. The governor of Puerto Rico's here. Hello, is the governor of Puerto Rico in the office? Have her wait. I'll be right back after my course. She is. Mucho gusto. I'm practicing my speech. So the cosine, here we go from this pi over 2 and pi. The cosine gives a bijection between 0 pi and the numbers between -1 and 1. So since by Cauchy-Schwarz this number lies between -1 and 1, I can write it uniquely as cosine theta. That tells, yeah, I need a theory of the cosine function.
Okay, but I mean, how do you develop the theory of the cosine without first?
A vector space? Wait, come on. No. Cosine is a function on the real line. If I have a number, I can take cosine of t. But this says once I have the cosine function, and I know it gives a bijection between this interval and this interval, and I have a number in this interval, that's uniquely of the form cosine theta. And that's what I call the angle between two vectors. And then the law of cosines says that in 2 space, it works out to be the right angle. Okay, so we're going to pick up on Monday all the geometry we get by looking at Euclidean geometry from the point of view of this group. And it's going to be a completely different point of view. Here's a problem for you to just think about. We saw that these elements were in the orthogonal group. Prove that if you have an element in the orthogonal group and it has an eigenvector, then the eigenvalue is plus or minus 1. Namely, the only things that could be on the diagonal are plus or minus 1.